Hi, my name is Sabine Plummer, and I am a final year chemistry student at Concordia University. And this past summer, the Natural Science and Engineering Research Council afforded me an undergraduate student research award, which allowed me to undertake a research project in Professor Ashlee Howarth's research lab this summer. So today I'm going to take you through my project, the synthesis and characterization of MOF UPC-68, and tell you a bit more about what I did. So first and foremost, what is a MOF? A MOF is a metal organic framework. So it's a network of inorganic nodes and organic linkers that form a periodic framework material. It's like a molecular sieve or a very, very small sponge. And what's particular about this is that they have incredibly high surface area. They're porous and often crystalline, and because of the amount of different metal clusters and organic linkers we can use, they often have tunable structures and pores that we can functionalize for many different types of applications. My project was on UPC-68, which is a very specific MOF. The MOF in particular has a hexanuclear rare earth center, which means that these centers are made up of 6 rare earth metals. It has a THEA topology, which is shown in the lower section of the image over here, and are 8 connected. So that means that the metal clusters are connected at 8 different points to the linkers. So what are the rare earth centers used? So the rare earth centers, the rare earth elements, I should say, are actually at the bottom of the periodic table, often known as lanthanides. In this case, they have unique fluorescent properties because of the unfilled electron orbitals. And they also have very similar topology geometries to zirconium clusters, which are very commonly used for very stable types of MOFs. Usually in zirconium clusters, we use 12 connected centers, which are very saturated and stable. But in the case of my MOF, we use 8 connected, which means that they are not saturated and are thus a lot more unstable. One way to fix this and mitigate this issue is the type of organic linker we're using. And so due to the decreased stability from what you would expect from a 12 connected, we use the H3-CTTA linker, which the long name I've listed at the bottom over here, 4,4,4,2,4,6 trimethylbenzene, 1 through 5 triyl tribenzoic acid. The HC3-CCTTA is a much shorter name. Also, sometimes TMTB is used. And this allows for a much more rigid structure because of the methyl groups on either side of the central benzene ring, which keep the longer arms from spinning. And so you actually get a steric hindrance, which limits the rotation of the longer carboxylic groups. And so this helps stabilize the 8 connected centers. It also favors the THEA topology due to the entropy effect. So what are the objectives for my project? First and foremost, I have to synthesize the linker since it's not readily available to buy. Usually we try to synthesize these with an above 65% yield, just so we're a bit more greener in our use of chemicals. I would then try to synthesize the series of UPC-68 MOFs. So a few of them have been published in the past year, I think, but you saw like all the lanthanides. I would try and make all of these different MOFs with all the different metal cluster centers. Then to characterize a series, there's a long myriad of tests that can be used. And finally, the applications can be tested for these MOFs. The published and reported applications have with nitroaromatic recognition and iodine absorption capacity. I have a personal interest in organic dye absorption, so I would be looking at possible applications within that realm of possibilities. So first and foremost, the linker synthesis. This is what I spent the majority of my summer project doing. It's a very, very long synthesis that takes about, on average, 1.5 to 3 weeks to complete. The first reaction is actually light and oxygen sensitive, so it has to happen under nitrogen atmosphere. It has a 72-hour reaction period, so it takes 3 days to get through the first step, after which there is a product isolation, a liquid-liquid extraction, and then a gel column, which takes on average 8 hours if it isn't pressurized, followed by then 12-hour-long reflux period, and finally isolation, filtration, washing, and drying until we can use the linker. And so the beginning of my summer was very much trying to make this linker and also making the synthesis as productive as I could. So my first attempt, sadly, went wrong out of the gate. One of the septums that was attached to my reaction vessel popped due to the N2 atmosphere being a bit too high, causing all of my liquid to evaporate and my chemicals to oxidize. So sadly, I had to start all the way over. But at least we were only 2 days in that first time, so it wasn't that big of a deal. My second attempt went much better. A couple of things that we noted when we were looking at the results was that part of the catalyst that is used during the initial Suzuki coupling, which is the first reaction, did oxidize. So we did have some manipulation mistakes that we would have to rectify in our third attempt to limit the oxidation of the chemicals. Also, we noticed that during our liquid-liquid separation, which is the second step, it wasn't a complete separation. We were still seeing some discoloration in the aqueous phase. Also, during our column use, we used an ethyl acetate to hexane mobile phase, which is not what was in the original published procedure, just because we didn't have the right chemicals on hand. So it wasn't the best, but we made do with what we had. And when we ran our chromatography column, we ended up with 4 different isolations. And so at the top over here, you can see a small thin layer chromatography, which is a very handy little tool to use when we're trying to identify different isolations from a larger complex sample. And it allows you to kind of look at various separate fractions from your column individually and see what from the original sample you have managed to isolate. And so in this case, we see that we have 2 bands that are our initial, our starting reagents, followed by the product that we are looking for, which is an intermediary as we try to get our linker. And then finally, some leftover byproducts right at the end. And so the band that we are looking for is that third band, the very bright blue spot. So it was under UV light, it was very bright. We also noticed that it left kind of like a white residue on our test tubes. So at the bottom image in the 44, 45 fractions, that what you see there. And the last isolation, we weren't sure what it was, but it did have some kind of yellow discoloration. So it seemed to be kind of probably a byproduct from the initial reaction that left a kind of oily residue. So we tried to limit our fractions to specifically the bright blue points. We also ran an NMR of those fractions. So in this case, 35 to 55 in DMSO at 300 megahertz to yield the top spectrum. The bottom spectrum is from the initially published paper. And so you can see a lot of happily associated peaks. So we can definitely see that we did manage to get the product that we were hoping. We do have some other chemicals within our product. There's a few peaks that we could not assign and that were most likely impurities. Considering this is just an intermediate step, we tried a couple of things to try to get the impurity out successfully. So in the end, we just decided to run with the next step of our reaction, hoping that it would wash away any impurities and we would get our final yield. At this point, our yield was very, very low, but for a first attempt, it wasn't half bad. We already knew some of the things we wanted to rectify for the next time around. So we decided just to see if we could get to our final product from the get-go. And we did actually. So this is the final NMR post the hydrolysis, which is the last reaction step, and then the isolations and drying. So you can see I've assigned the NMR peaks to our final linker, and there's also just a small little picture. There's not much in that little vial, pretty much had to scrape down the sides for it, something like 7 milligrams, I think, in the end, which is just impossibly low yield. But it did wash away our impurities that we were kind of worried about at our intermediate step. So we knew that the overall procedure that we were using was sound, and we did get the linker that we were hoping to get. However, in quantities too low to use for anything, really. So the next step was then to do this again with our different corrections to the procedures, as well as a higher amount of initial reagents so we could get a larger batch of linker. Some of the things that we changed was that we used a transfer procedure during the initial N2 atmosphere reaction that didn't expose our reagents to oxygen. So this limited the oxidizing of our catalyst. We also used chloroform during our liquid-liquid separation, which yielded a much better separation. This is a bit kind of trial and error. We tried different chemicals within the same family that we could, just to see which ones better interact with our product. That went really well. We also dried with magnesium sulfate before we ran the column to try to get more water out. We had a very strong water peak in the initial NMR, so we wanted to limit that. And we also finally ran the column with ethyl acetate and petroleum ether, which was the recommended solvent from the initial paper that we didn't have on hand the first time, but this time we managed to get one of the labs, the organic labs next door, to give us a bottle, thankfully. We again got 4 isolations, and there's actually some interesting little videos here where you see the actual bands in the column starting to separate. They're not visible to the eye, but they are visible under UV light. And so this is what you're seeing. We got a new light bulb for a handheld UV, which I didn't have the first time around. So in this time, the column was much easier, and you can see the bright blue band, which is the one that we're hoping to get. And so this time around, we got somewhere around 70% yield of our final linker, so not even the intermediate. This is right at the end, after the 3 weeks worth of synthesis, we have our final linker. We did have a couple impurities, some water still, but overall it was exactly what we wanted. So with this new batch of linker, we were able to move forward with our MOF synthesis. So how do we make MOFs? So MOFs are made generally with a kind of like a standard procedure. All MOFs are kind of a put everything into a small little vial, shove that in the oven for a couple of hours, and you have it. In this case, we put our linker, the rare earth metal center that we choose, so one of the lanthanides, dimethyl formamide, which is the solvent, 2-fluorobenzoic acid, which is kind of coordinates the MOF synthesis, acetic acid and water as well. These ones go in the oven for at 120 degrees for 72 hours. So again, more wait time. Once they are done, we let them cool off and we transfer them to centrifuge tubes for the washing process. So we wash them with new DMF, or dimethyl formamide, to clean them out. And then we wash them with acetone to clean out the DMF. And then the acetone dries out and we have MOFs that we can use. So, sorry, you can see a couple of images under the microscope. So these are right out of the oven, put them under a microscope to see what they would look like. And sure enough, we get small crystal cubes, clear cubes, which is what the original paper stated we should get. So it looks like we achieved to make a UPC-68. I have ytterbium, europium, and terbium over here. My third batch of linker allowed me to make a little bit of each of my lanthanides that I wanted to make, very small amounts, but they look like a lot under the microscope, of course. And so we have these beautiful little crystals that look great. We also put them under the scanning electron microscope to get a kind of closer look. And so again, we see this beautiful crystalline structure, these really amazing cubic MOFs that are going to be very exciting to work with as we move along. And so this one is the holmium sample that I made. So what are the next steps? Well, we managed to synthesize the linker with an above 65% yield. We managed to synthesize my series of MOFs, not just the published, but also some of the unpublished ones, like the homoium that you saw earlier. I've ran a couple other characterizations that I didn't share here just for time and also interest. I know NMR spectras aren't the most interesting to look at. So I ran NMR, SEM, and PXRD on these. I'm going to be running nitrogen sorption soon, as well as some other interesting things. And as I kind of work through those, I'll probably have to synthesize more of the linker and more MOFs just to have enough. A lot of these characterizations do require higher amounts than what I currently have on hand. And then finally, once that's all done, we can look at testing the applications. So just a little acknowledgement slide. I want to say thank you to my supervisor, Dr. Ashlee Howarth, as well as the graduate students, Paola Marino and Victor Quezada, who have helped me with my project over the summer, and everyone at the Howarth and Majewski research groups that have been very helpful, as well as NSERC for allowing me to do this project. Thank you.